much. It's a real pleasure for me to be here. I have only one problem, actually. I have too many slides. When John asked me to talk, I thought about what I should talk about. I could have taken the possibility to talk about recent work. We are working on a number of more focused topics. But then I decided I'd rather give you a kind of an overview over the work we did, and some of the work you will see that is already a few years ago, because my intention is to give you an idea of what I mean by seamless modeling. I'm interested in modeling in software and systems engineering. As John told you, I'm from a department of Informatik. You would perhaps say computer science or computing science. There was this discussion for a while. I like the term informatics a bit better because it means that it is a department we talk about everything which has to do with information and information processing systems as part of larger systems. And when we look at those systems and software in systems, we have to talk about a number of aspects. We have interaction, we have distribution, we have to consider the context, the system's operational environment. We have to talk about physical issues like real time. An interesting question is probability there. And we do that by a scheme we have developed over the years. We believe that when we want to model systems, we have three main concepts of systems we look at, which are interfaces, state, and architecture. And I will take a very radical point of view. I say, this is all what you need. Now, what is seamless development? Because I use this word in my title. Seamless development to me means that you do development by creating a chain of models. You don't have just one model, you have a number of models. What you need is a high expressive power. The idea is to capture all aspects of systems in these models. You have a tight integration of these models into your artifacts. What I mean by artifacts means a documentation of your engineering process, and you have a clear understanding what the roles of the different models are. And so development steps, at least in principle, from maybe the first side, very academic point of view, but in the second side, also a practically interesting view, is that you understand the development step as a change in the model. Change can be many things. Adding something to the model, revising the model, changing the level of abstraction. And then you have to understand the relationship between models, like refinement, decomposition, change of scope. In my field, in software engineering, people use a lot in practice approaches like UML. In system modeling, people use modeling language like SysML. And I will say, from time to time, I will say a few critical words about those approaches, because I think they don't manage to capture a number of important concepts needed. For instance, one important thing is you have to understand how different models relate to each other. So you have to understand the relationship between different models for more or less the same system, and you have to understand how to integrate models. So you have to understand how different modeling views work together. And those things are not at all worked out in your system. And of course, we are in particular interested to do this more perhaps fundamental work to get an extended tool support with a high automation. And I believe on the long run, we will do system development completely supported by tools which work with what we call also development backbone. Roughly speaking, databases in which all the details of the things you worked out during development are put into the databases which have a clear structuring, and where you can have traces and links between the different development artifacts. And we are working with some companies. I think the most impressive work which is done in practice currently is done with a German truck company with its basis in Munich, which you might know, which is MAN, a drug company which is, at least from my point of view, most advanced in this approach. But my talk will today be very fundamental, just concentrated on the different modeling concepts and how they are related. We understand the system always as something which has to be seen in a context. So the system interacts with its context, its operational environment, including people, including other systems, and including the physical world. And interesting is the question where you put the boundary between the system. Here you have your system, and you have to decide which part of the world is the system, and what are the boundaries to the other parts, which part of the rest of the world is relevant for the system, and how is the interaction. And this leads to our basic notion, what is a, for the moment, discrete system model. This is a result, looks very simple, but it's a result of many, many years of discussion, not only in our department, but also with other colleagues in other departments. And we had many, many very stimulating discussions also with mechanical engineers or electrical engineers. What is a system? It's a very complicated notion, by the way, because if you look at the different disciplines, you can also ask what is a system in biology, or what is a system in economy. I'm much more concentrating on systems of the type we are interested in, namely devices, which have certain functionality. So we came up with the following definition. A system, first of all, has a boundary. So we have to have a clear understanding what is part of the system and what is outside the system. If you look at physical systems, often it's not obvious where the boundaries are. So often it's your decision to say, I take this boundary, and if you do this decision, you have identified which systems you are talking about. The next thing you have there, which I consider as a major notion, is interface. In a lot of the modeling approaches you see around, the notion of an interface is underrepresented. For instance, if you look at UML, in SysML it's a bit better, but if you look at UML, there is no clear notion of interface, which I think is a major drawback of UML. Now, what is an interface? An interface basically characterizes what kind of interaction can go on between the system and its environment. And if you're interested about understanding the functionality of the system, this is the only way you can do that. Because you have to study in which way is the environment influenced by the system, and in which way the system, the environment influences the system. So, and we do that from a modeling point of view by introducing a static or syntactic interface, which talks about, at the moment I talk just about discrete systems. So you talk about the events that are in principle possible at the system boundary, and then you have something which I call interface behavior, which talks about the logical dependencies between the events. And this is the first, from my point of view, from systems engineering, most important point of view into systems understanding their interfaces. And then you have, some people would call that the black box view onto a system. Then you have elements of a glass box view on systems, where you look inside a system and want to understand its structuring, subsystems, which gives a subsystem architecture. Of course, also a major question in system engineering, and you talk perhaps when you're in discrete systems about states and state transitions, and you get a state view. And these two views are complementary. You can have both an architectural view and a state view for the same system side by side. And there are other systems like quality profiles and so on. I will not talk about those. Now, on this slide, I will give you first of all, the idea of the interface technique we are using. So this is interface behavior as a key concept. Again, we talk about discrete systems. And here you have the system, you have the boundary of the system, and the syntactic interface is given by channels. Each channel has a name and a type. And the channel is a communication link or an interaction possibility in which you can, which certain events or data or signals, whatever you like, may flow into the system. We have input channels, or where the event signals data may flow outside of the system. So we get a pure data flow onto the interfaces. And so the syntactic interfaces is described by two sets. It's a set of input channels, names and types, and a set of output channels, names and types. These can be connected in Dutch, what we call a syntactic interface. And now we have to talk about behavior. To talk about behavior, first we have to have a notational description of the semantics of a channel. Well, a channel over a span of time, and we consider an infinite span of time starting at the time point 0 till infinity, which can be understood as a sequence of time intervals. If you give each time interval a number, you can model time by the natural numbers. And for each time interval on each channel, we can observe a finite sequence of messages of the type of the channel. And therefore, we can define a stream over a given type T as a mapping from the natural to finite sequences of messages, elements, events. And if we have a set of channels, we can just associate with each channel in the set such a stream. This gives us what we also call a channel history. And now we can already define the behavior of a system. What is the behavior of a system? It's a mapping between the history of the input channels to the histories of the output channels. And since we are interested to also deal with what some people call non-deterministic systems or underspecified systems, for each input history, which means giving a stream of data for the input channels, we associate a set of possible histories for the output channels. And that's all for the behavior. And if you want to talk about behaviors in interface specifications, then I will show you more about that. This is simply done by a predicate that talks about in a logical formula about the relationship between the input and the output channels. This is a basic model we are dealing with. There are a few things more to say about that which will come, but we work with this model now for many years. We like the case that it's very simple, that it's easy to explain to engineers, and it's in a sense quite powerful because it includes already time. So the model has time, in this case discrete time, as a built-in concept. And here you see, I will also give you always the literature where you can read about that. And if you're interested, of course, you can have the slides and look at the references if you're interested. Just to explain what I already explained is, if you want to model a system consisting of a number of subsystems, now we can do that by having these boxes, which are the systems. They have names, and they have channels, and the channels have also names. This is what we already saw. And just to explain a little bit this idea of the timing, on each channel we consider in each time interval a sequence of messages. So this gives the classical basic idea how systems interact over exchanging messages by channels. So we go completely away from any ideas of shared memory, which was, from a programming point of view, often an approach to modeling systems by just modeling the interaction between systems by exchange of events, of messages, or signals. So that's the basic idea. And just to repeat that, I already said that, if you have a set of channels, we give a type to each channel, we can give a history to a set of channels, and I use this to denote the set of all histories over a given set of channels, or sometimes I use a C with an arrow also to write that. And so we have the system interface model. Also here you see nothing which is new, just what I introduced so far. Syntactic interface and semantic interface, a mapping between the histories of input channels and sets of histories of output channels. And the system is deterministic, if for each input history is a set of output histories and exactly one error. So this is extensible. Any questions here? If you have anything you would like to ask, please just interrupt, because it's much nicer if we get into a discussion. Everything's fine so far?
Yeah, the basic I would say the interfaces are dynamic consistent.
Yeah. And now, we talked about time. Now, I've introduced the model of time, but this is of course not enough. I also have to reflect the role of time in a semantic property. And here's the semantic property, which I call strong causality. Strong causality says the following. If I have a behavior here, this behavior is strongly causal, and this is what all systems should at least have a kind of causality. I just tell you then the difference between strong and weak causality, but let's just look at the strong causality thing. It says the following. If we take an arbitrary point in time, and if in two input histories, X and Z, and if these input histories are the same until T, mathematically simple, this arrow down just takes out the prefix of the history X of next T, so it's just the first, what you find in the first T time intervals. And if the two histories coincide in the first two T time intervals, then the requirement is that the set of possible output histories of this function f on x and on z until t plus 1 are the same. That's causality.
This is a master clock.
So yeah, it's a master clock.
What happens when you don't have a master clock?
Then you have to model local time, which can do on top of the master clock. But the real thing, what happens if you don't have a master clock? You're lost. If you don't have physical time, you're lost.
Or are you generic?
Generic. Because otherwise you have no chance to talk about the time. No, this is the basic idea. This is causality. Weak causality means that you just drop the plus 1. What does the plus 1 bring you? Yeah, but the separation between past and future you also have if you drop the plus 1, if you just write the same thing, just a t here. But that's what does the plus 1 give you? Sorry? Delay. Yes. It models delay. It means that you get only the answer after one delay of time. And this is a very interesting question. I'm not sure whether you studied the work of Gerard Berry with Esterel. He had this idea of immediate reaction. So in his system model, things would not be strongly causal but only causal. I call a system causal if the same formula holds without the plus 1. It has a lot of consequences for your modeling approach, having strong causality or just causality. If you would drop causality, you would get system behaviors which are not realistic. You could have a system which predicts the future. So causality means systems depend only on the input they have seen so far. They cannot depend on input which comes only in the future. Strong causality means the output is delayed by one time step. We will see the consequences of everything. Questions here? And that's all. This defines what I call interface behavior. Now let's just look at some variations. These were discrete systems. Now let's look at continuous systems. The important thing is if you go to continuous systems, you have only to change a little bit. Only the red stuff is changed, which means you just go from discrete time to continuous time, which are the reals. And everything what I discussed so far can be carried over to the continuous case. You can even mix it, then you get hybrid interface behaviors, and therefore, and this is something which I want to emphasize in this talk, which this is exactly what I call seamless. You have a modeling idea, and this modeling idea can be extended into different directions. One direction to extend it is a continuous part, and then you go into control theory, and then you have lots of things to study there, but in principle you can have an interface model for continuous or hybrid systems.
Where is event trigger in this?
Event trigger is here. This is already event trigger. The first thing I introduced. Sorry. The first thing I had, which talks about this discrete systems. And now we have continuous systems. The thing we looked at recently, last year or 2 years ago, the PhD thesis was finished, which I found very nice result, is to extend it to probability. And again, only this red part is the change you have to do. Remember, I now refer again to the discrete part, we consider behavior as a mapping from histories into sets of histories. If you want to study probability of systems, it's utterly simple. To work it out mathematically is not so simple, but the idea is simple. We'll introduce, for each input history, on the set of output histories, you introduce a probability distribution. And it's a straightforward extension, which we found very nice. So you don't have to change a lot. You just say, if I have a non-deterministic view on a system, I say, for each input history, I can study what are the possible sets or the possible output histories. And if you're interested in probabilities, you ask, what is the probability to get one of those? And I will show you a little bit of that. The whole approach, or the whole modeling approach, can be extended in a very conservative way. So conservative means without losing any of the nice properties from a non-deterministic view to a probabilistic view, which is very helpful, because then you know that you can deal with systems, just a second, that you can deal with systems, if you like, from a non-deterministic perspective, and go to the probabilistic perspective every time you want. Right?
Yeah, so I had a question about your, when you move to the continuous modeling, it looks like instead of having sort of a continuous analog of sequences of messages, you just have a single value at each of the continuous time points. Is there a reason why you made that?
I didn't take enough time to explain it in detail, but what you would rather like to see that you have a continuous function there, a function in time. Mm-hmm. So it's classical what you find in differential equations in mathematics.
Mm-hmm. Excuse me?
Yeah?
Can you please explain how you can always move from non-determinism to probability? What if you don't know the probability?
Oh yes, what I said, you can always do it by the mathematical modeling concepts. You ask the question, if I deal with a real system, how can I capture the probability distribution? That's a set approach. But the argument is just, you have a possibility to talk about them without having to change your model completely. And it took us some time, also my PhD student, he had a hard time in the beginning to understand what is the relationship between non-determinism and probability. And this was one of the results to have a very clear idea there.
So I'm not sure I understand the answer. I'm sorry.
I think there are two issues. One issue is, what are your modeling concepts to model systems? And what I showed you is that you can have modeling concepts where, if you study a system in terms of, let's take a simple example. If you want to model a telephone system, and you want to model your telephone device, then in looking at your telephone device, you might do it very non-deterministically. So if you call someone non-deterministically, either you get a connection or you get the result that a connection cannot be given. Then at a certain moment of modeling, this is just fine. But later you might be interested in saying, well, I wouldn't like to have a telephone where that I don't get the connection is happening too often. And then you say, oh, now I introduce a probability requirement, and I say my requirement is that the probability that I don't get the connection is below 1%. So you go from a non-deterministic modeling, in which you can do a lot of proofs, you can justify what you have specified. Then you go in the direction where, in addition, you introduce probability. And what I mean is, all the results you have so far are still valid. They don't just talk about probabilities, and you get additional possibilities to talk about.
Non-determinism is not general from probability, so clearly it is very.
Yeah.
So,
But the important thing is that you have a homogeneous model in which you can talk about things from a non-deterministic point of view and a probabilistic point of view. And in particular, if you deal with safety, this is very helpful. Because if you deal with safety issues in systems, at a certain point you want to prove that certain things are logically true. And later you find out that there are some assumptions which show that you have faults, and then you need fault models, and the fault models you will put rather introduce probabilities.
yeah, relevant, only if you know the probability. If you don't, then.
Well, no. If you look at the safety analysis as they are used in practice, they don't know the probabilities, they have estimations. Why is 10 to the minus 9 a good goal in safety on airplanes? They don't know, they just estimate.
So that you're arguing that you should probably would be.
No, it gives you a model in which you can carry out those estimations. You can write specifications and you can do logical proofs about probabilities.
Sorry.
Yeah.
So when you say that a telephone is non-deterministic,
Yeah.
what does that mean? So I place a call? What do you mean by non-deterministic?
Non-deterministic means that you wrote a specification, it's just a model. Not the telephone is non-deterministic, it's a model you have for a telephone is non-deterministic. And you say, I model a telephone by giving all the possible behaviors which I would allow, without saying something about how probable they are. And then I can reason about, if I have a lot of those descriptions of systems, I can do a lot of reasoning what's possible and what's not possible. But I don't know anything about probabilities. And when I introduce later probabilities for certain of these behaviors of systems, and then I can enhance my argumentation by arguing about probabilities. That's the point. Yeah.
And who reasons these probabilities, or who estimates?
As you see, look at safety analysis you have in practice, people look at that and they do probability estimations.
So let's say for a phone, like
Yeah.
you send a group text message and you don't know how many of the people will reply. How do you, who estimates that?
Yeah,
From the telephone line.
there are some, if you are a telephone engineer, you would look at your statistics and you could find it out from the statistics. If you are electronic hardware engineer, you look at the probability that some device fails within a certain amount of time. So you can take in data from real life. And then you take your data to your models and then you reason in your models. Not so surprising. The next extension, which we did a bit of work but not enough, is to extend these models to more physical aspects beyond time, like space, geometry, temperature, so there's a lot to do there. The next step is I want to go into issues of specification, refinement, and the important notion there, of course, is compatibility. What you have seen is interface specification, and if we have such an interface specification, so notion of interface, we want to do interface specifications, and I give you a simple example here. I keep it simple, but it can be done for much more complicated systems. Let's assume we want to specify in the model of discrete systems a behavior of a transmission component. You see, the transmission component takes an input channel, which is called X here, with some messages of type T, and produces on an output channel a stream of messages also of type T. The input channel is called X, the output channel is called Y. This is the description of such a specification. In the description, we first say what is the input channels, what is the output, and the types. By the way, in the graphical representation, you have exactly the same information. And then you have what we call a interaction assertions, or interface assertion. which describes the relationship between the input and output streams. And here you see the mathematical formula, which explains this twiddle notation. X twiddle y is explained as, for all messages, we require that the number of copies of the message is X, and the number of copies of the message M and Y are the same. Keep in mind that in addition we require strong causality. And this gives you a very simple system specification, which just talks about the messages in the input streams to describe behavior. What kind of behavior is described by that? What kind of system is it?
What portion time?
Sorry?
What portion time you allow?
You mean what time I do allow? I can do nothing say about time, only strong causality.
Okay, so what portion types of system you allow?
What types here? Any messages, assume email messages, just to make it simple.
So you can reorder messages, but they, on the output vis-a-vis the input?
The thing is, this system can rearrange the order of messages. According to strong causality, of course, you can receive messages only after they were, you can send messages after they were received. The order can be changed, and what is important is, even with an infinite number of messages, you are guaranteed that every message that is sent is received. And as every message that is received or sent. So it's in a certain sense, it's a perfect transmission. It has safety properties and liveness properties.
No failure.
Sorry?
No failure.
In this case, no failures. You could think about a specification where you specify failures. My point is, it is a very straightforward logical description of behavior of systems. If you like, take your favorite system description technique and try to describe a system like that. Temporal logic, state machines. It's very difficult to describe a system like that because it has sophisticated liveness properties and it has safety properties. And my argument is, we try to keep it as simple as possible just by writing these simple relationships between histories, which has a number of advantages. And here the specification, of course, has a specification name, an input channel, an output channel, and specifying interface assertions. Now here you have an example of a safety property and a liveness property, which says here, if I receive a message, the specification guarantees that the message was sent. Or liveness property, if I send a message, the message is finally forwarded. And by the way, what is also remarkable, these properties can be immediately proved from the assertion I've written by general higher order predicate logic. So you don't need a special logic. This is not non-classical logic, absolutely classical logic. Interesting is also composing interfaces. If we have two interfaces, we want to compose it. To keep it simple, I do it in a graphical way, then you see what I mean. Of course, you can compose many components. I just give you the formulas for two components, because if you can compose two components, you can do that for a finite number of components. We have component F1 and F2, both have input and output streams and channels, and if we compose them, we just compose them in a way that the output streams of the first component, which are with their names identical with input stream of the second component, they are connected and vice versa. This requires, of course, that there's a certain consistency in naming the channels, but this gives a very simple way of composing systems. We can form architectures that way, but the interesting question is, given two specifications for the subsystems, how can we calculate, how can we derive from that the specification of the composed system? And here it is. We put them together and we get a new system behavior, interface behavior. This is the remaining input and output channels, which are not used as internal channels. And how do we get the specification of the overall system? Well, we take the specification of the first and the second system, put these two specifications by a logical order, and hiding is done by existential quantification. This is very simple, but we worked hard for a while to make sure that this is exactly doing the job as it is. Remember, I had acquired strong causality. Strong causality is the key here, because if you have strong causality, you can prove that this formula reflects exactly what's operationally going on. So you can prove if you have an operational description of the component by, say, state machines, and you put state machines together that way, and if the two state machines has this property S1 and S2, then we get for the composed systems this property. So this is a correct way of composing, and it's a modular way of composing. By just knowing the interfaces of the two systems, I know the interface of the composed system. And the third remarkable thing is what's happening in system composition is exactly reflected by logic. Parallel composition is at the specification level logical, and hiding is at the specification level existential quantification. Right?
Yeah, so with this operator though, it's not going to be associative, right? If you have to, because the order in which you do the hiding is important.
That's right. It's not associative in the sense that if you have name clashes, then it's true. If you do a very simple assumption that you make sure that you have no name clashes in the sense that it's associative. So it's close to associative. Any other remarks? And it's modular. I tell you all again my definition of modular. Modular means from the interface behavior of subsystems, I can construct the interface behavior of the composed system. And there's a second thing which is remarkable here. I can study the systems exclusively in terms of mathematical logical formulas. This formula catches completely what's the interface behavior of this component. And therefore, I get a complete logical view of the systems. I will come back to that later. Now I can do refinement. I go a little bit faster over refinement because this is something which is, I think, known. Refinement means I have to relate. So the idea of systems refinement is that systems are developed in a sequence of development steps. So this is very close to what I said when I talked about seamless behavior. The refinement relation is a relation between system descriptions, more precisely system behaviors, and they can of course easily be expressed in terms of this interface assertions. And we study two notions of refinement, and I will not go into details. If you're interested, you can read that in papers. The first notion is very simple. This is what we call property refinement. We have two behaviors, and f hat is a property refinement of f if the set of outputs of f hat for each input is a subset of the set of outputs of the other input. At the logical level, it means we have implication between the interface specification of f hat and f. But this is very classical, so I don't think I have to talk about it. What is nice is we can just take refinement as it was developed in the 70s by people like Wirth and Moore and Dahl and Dijkstra here. The more remarkable thing is that also this property refinement is compositional. If we have a refinement relation between subcomponents, this guarantees a refinement relation between the architecture built from the subcomponents. This is a key. If you don't have that, you cannot do modular development.
Can you give an example or just clarify this a little bit? This guarantee that if you have this type of compositionality, that you can carry over module, you can infer behavior of the module, so as you refine
And
it?
the idea is very simple. If you assume you have an architecture, and the architecture is done by describing the subsystems of the architecture by logical formulas. And now you want to define your subsystems. When you define your subsystems, of course, it's important that a refinement of a subsystem always means that you get a refinement of the overall system. which means that if you do independent steps of refinement for your subsystems, you never go away from refinement of the general system. That's the basic idea. And this is not true for many calculi. There are a number of calculi where this doesn't hold. So it's an important property you should have when you do system development. The next notion is a little bit more complicated. It's a vertical refinement, changing levels of abstraction. I just give you the idea, and I will not go into the technical mathematical details, which take a little bit more of time. Assume now you have two systems which are at completely different levels of abstraction. I take a very simple example. Assume you have a system which does arithmetic. And one way to describe it would describe it that it works on streams of numbers. So F takes two streams of numbers, and maybe it's an arithmetical device which gives the sum and the product of these numbers at output. And then, of course, you would like to do a very technical description of the system, which works on sequences of bits, streams of bits. And you can have a parallel arithmetic unit or a sequential arithmetic unit, which means that you either have many channels, where you get a description of a number by the bits you get in parallel, or you can have a way where you get the bits sequential. In any way you can describe arithmetic also there. Now the question is this bit level description of arithmetic a refinement of the number level description of arithmetic? And by the refinement I've introduced so far, it only works if you have the same syntactic interfaces. Now you have changed the syntactic interfaces completely because you have different channel names, and different channel types. How do you deal with that? Now the result is the following. You introduce a set abstraction and representation functions both for the input histories and for the output histories, and the rule is as follows. You have this abstraction and representation function, and now you require that f hat is a refinement of what you get if you apply the abstraction function, calculate at the abstraction level, and then apply the representation function. This can be explained nicer in the graphics. If you have an input history, you abstract it, you do the abstract calculation, you represent it, and the outcome must be a behavior where f hat is a refinement of. And this is a very powerful refinement notion, which allows you to capture all kinds of refinement you have in real life system development, because there you often change the level of abstraction. And
That's
this
not
gives you
two conditions on A1.
Yeah, I didn't read that. The conditions of A1 and A2 are the following. That if you calculate of an abstract history, the representation of the abstraction, again you get the identity. And those, it's a classical generalization of data refinement. And these are the powerful refinement notions you need to have this seamless development, and now you can prove a number of properties like compositionality, and that it distributes over composition and many things more. In the end, if you want to do it at a very theoretical level, you can prove that interaction abstraction, interaction refinement is a Galois connection. And then you can introduce a notion of compatibility, but this is already what we have. What is compatibility? It's very important for systems engineering. Compatibility means if I have a system and a subsystem, and I want to replace a subsystem by a refined, different subsystem. What do I have to know to be sure that this replacement does not change the overall behavior of the system or does not affect the correctness of the system? Well, this is compatibility. We can show that compatibility coincides with refinement in the case of modular refinement. I talked already about time. I don't have really to talk long about it, so I switch over it. But just what we did a lot of work of relating continuous time and discrete time and understanding how these time models relate to each other, and exactly what you asked. If I have different timings in subsystems, how can I relate timings with different subsystems? So we have developed a timing calculus for that. And of course, we can now write more specific timing restrictions. This is just the old example TMC, but now I say message cannot be wait arbitrarily long, but I can introduce finite delays. This is just to show you the formulas.
Does time flow uniformly?
Yeah.
What happens if it doesn't?
Then you, as I said before, you could say the physical model of time flows uniformly. And if you want to have specific notions of time in subsystems where you have, for instance, clocks which are not accurate, then this can be modeled by introducing a second notion of system time on top of this global time which was introduced. But this is...
So it's always, I think, the idea of a third agent in this sense, right? That's what we had before as well.
Yeah. I was very big on that. You can introduce state machines. This is very typical. You can write state transition diagrams. You get a communication model of state machines. You can then introduce a notion of computations. I'm sorry to be very fast here. You can introduce then an abstraction, an interface abstraction for state machines where you associate with each state machine an interface behavior. Then you can prove that strongly causal machines are Moore machines. And then you can also show that these interface abstraction for state machines can be at the logical level related to interface behaviors by certain proof calculi. And what is interesting is the following, that if you introduce then a notion of observable equivalence, you get a very important idea. Here I introduce parallel composition of state machines. I will not treat the formulas because this is interesting. This is an important law you have to have when you do modeling. This law says the following. If I have two state machines, and I put them together as state machines, and I do the interface abstraction, I'm guaranteed in the modeling approach that the result is equivalent to what I get if I do the interface abstraction of the state machines first, and then put together the interface behaviors. Why is it an important property of a modeling calculus? Only if you have that, you are free to decide whether you work at the level of interface descriptions or at the level of state machines. It makes no difference. So it gives you the freedom for engineering. By the way, this is an important property which you cannot even formulate at the level of UML. Because UML does not allow you to show how an interface view is related to a state view. Could use as state charts, but what the meaning of state charts is a real long discussion. So now let's just skip over the state machine. An interesting work we did is functional decomposition. I will give you the motivation for that in a minute. Today in our systems, we work a lot with the car industry. And with the car industry, we have, for a lot of the functions in the car, we have so-called functional feature interactions. What is a functional feature interaction? You have a functionality in the car which you would like to understand as a separate functionality, say air conditioning. And you have another functionality in the car which is a separate functionality, say braking. And then the question is whether there is a kind of a dependencies between these two functions. So the question is, can your air conditioning system in your car influence your braking system? And the answer is better not. In fact, there were cars produced where this was the case. And I could tell you a long story about that. I will not do that. I will just say we were interested in understanding how could we understand a large system like we find in premium cars today. A BMW has today about 4,000 different software-based functions. How can we understand these 4,000 functions as independent functions and nevertheless understand how they depend on each other by feature interactions, which, as I formulated, is a contradiction by itself. And so we have developed the following approach. If we have two functions in isolations, which can be described by interface behaviors, and we put them together, this is simple. But if we put them together this way, we have, of course, guaranteed no feature interaction. But in many cases, we want to have feature interactions in systems. What would be an example of a feature interaction in systems we want? Well, if you drive your car, you listen to some radio, and then a telephone call comes in. You are used to that the radio is stopped. You don't listen anymore to the radio, and you can do your telephone call without getting disturbed by the radio. This is a wanted feature interaction. Because the telephone function, which is a separated function, influences the radio function. Now, if you do a combination like that, you couldn't do that. So we introduced what we call modes, operational states, which are modeled by messages which are exchanged between the functions. And then we can go from isolated steps in steps where functions have interactions. We take a function, we do a kind of refinement, which is here, where we allow these additional interactions and we put them together in the way it is shown here. So we combine in a kind of refinement, and we have a very clear relationship between a function as part of a function, a larger system that way. And this allows us to get a completely functional view onto systems. Now, in the car industry, there's a lot of work going on trying to do their work in that direction because they have a lot of trouble with feature interactions. We have a lot of non-well-understood feature interactions in cars. And now, having introduced all these notions, we get a very interesting possibility. Now we can specify a system from 3 points of view. Requirements, which are just a collection of logical statements about a system. A functional decomposition, where we introduce a number of predicates describing functions. And since we have this wonderful way of putting systems together, we put these properties only together by a logical end. And now this property says, if we describe each function independently, together with their mode channels, as I've introduced them, and I do a logical end over those, they have to imply the requirements for the system originally. This would be the way to prove the correctness of the functional decomposition of a system with respect to the requirements. And so we get a function hierarchy. This is a functional decomposition of the functions of the system into subsystems. These dotted line channels are the mode channels, which model the feature interactions. And then we can do the model integration. As I told you, we have architectures and state machines. For both, we have interface abstractions. And so we can now integrate our modeling approaches by saying each architecture defines a interface behavior, each state machine defines an interface behavior, and therefore we can relate different descriptions of system behaviors. And this can be extended to the probabilistic views, or I have introduced so far, which I have explained at the discrete level, can be also done at the probabilistic level. And then we can go over to non-functional properties like safety and reliability, which can nicely be expressed in the probabilistic views. Here you see the full system perspective, which we are working now in the project. We say this is a perspective of a system at a certain level of abstraction. You have the system under consideration, which is interface behavior connected to its operational context. And then we have a system decomposition leading to an architecture, and the architecture together as a number of subsystems that interact and work together to provide the interface behavior as hopefully as specified. And this gives us what I call modular system behavior. And here I want just to put together what I introduced to show you how, from a theoretical point of view, a system development can be done, but it's less theoretical than it looks at the first time. We start with informal requirements, of course. This gives us a specification of the system interface behavior. Since systems if you want to specify the interface of the behavior of a car, no way. It's much too complicated. If you specify the interface behavior of single function in the car, not that so much problem. Each of these individual functions could be specified. If you want to do such a specification, you have to be able to introduce a mode concept that allows you to capture the feature interaction there. Now let's assume we have done that. Then we can go on and having now descriptions, this is just to mimic that by diagram. What we have described now, what's going on over the interface of the system. The next step would be design. We decompose the system into a number of subsystems. Here it's just to illustrate that. And now we can do an architecture verification. Before we have built the system, we can do an architecture verification. How do we do that? We have to prove that from the properties of the subsystems, composed in the way that I have explained, this implies the required system behavior or functional specification. Not easy to do in practice, but at least from a theoretical point of view, this is exactly what we have to do. That would allow us to prove the correctness of an architecture before we have built the system. Next, and again, looking at the illustration, which means we get from a description of the system and its boundary to the description what's going on inside the system. Here we get the input from the outside and the output to the outside, and here you see what's going on. And actually we can even isolate the behavior of the components and try to get in a systematic way from that the specification of the interface behavior of that component. Then we go to implementation. Now for each of these subsystems we have to derive implementations, if you like, state machines, and we have to prove that the properties of the state machines prove the properties of the interface behavior. And now we can do the integration. We put these implementations together and we deliver. And deliver means we prove that from the system as implemented, the properties as specified follows. Now from a mathematical point of view or a system theoretic point of view, if we have proved this, and if we have proved this, and if this is the definition of the system, this is for free. If I show that to my colleagues in industry, they say you are crazy. Because what I say, you don't have to worry about integration anymore. If you have proof that your architecture is correct, and if you have proof that your implementations is correct, then integration is correct by definition. Why is it not true in practice?
But you never have a demonstration.
Yeah. We have done some investigations at Bosch, for instance, in a PhD thesis, and my student had the task to find out what are architectural faults in the field. And he worked in the archives of Bosch, and we were grateful that we could look at the archives for several months, and then he came back and said, now, how many errors did you find in systems in the market which were architectural errors? And we said, I don't know. And I said, are you crazy? You worked for 4 months now on this topic. We didn't find out. And he said, well, the problem is they have no proper architectural description, so I cannot assign of the errors, which errors are architectural errors or implementation errors. And this explains what happens in practice today. People don't write proper specifications anyhow. They don't describe the architecture properly. In particular, you don't have a well description of your subsystems here. And then you have to implement the subsystems without having proper specification, which just means that you never know what correctness really means. Even if you do tests here, and you don't have a description of an architecture that tells you that the architecture is correct. And so, at this level, you discover all the bugs you have done here. And what is even more critical, even with the bugs you discovered, you cannot say this is an architectural bug or this is an implementation bug, because you have no proper description of the architecture. And therefore you have to go in long agile cycles and change your ideas about the architecture and the implementation until things fit together. And the interesting question is, of course, this is a very theoretical picture. The interesting question is how closely can you get to the picture? And the answer is much closer than people in industry think. And we have done some experiments with industry which shows that it is possible to go that direction and it's even cost effective. The next steps I will do very fast. This was all very theoretical. Of course, this can be also applied to a much more technical view where we look at system levels, where we have this abstract level we have talked about, functional view, a logical subsystem view, but then we could also look at technical views, but I don't have time to report on that. And finally, recent work we have done is on tracing, because if you remember, with the techniques I've introduced, you can represent everything here by logical properties. So you have logic properties here and here, and also at the functional level, and then you can introduce traces, which are links between requirements, the functional model, and the architecture, and then you can ask, what does the link mean? Because this is a logical statement and this is a logical statement, and then now you can study the logical relationship there, which gives you a very firm basis for studying traces. Finally, very shortly, our also recent work, how we deal with so-called promise and guarantee, assumption and promise specifications, where when we talk about a system, and now this uses all the techniques I've introduced. You have a subsystem, which I call a watchdog, and now you have certain assumptions about a watchdog, assumptions for the watchdog. You say, you assume that when the system is not ready, and you see the watchdog is saying when the system is ready, the rest of the system guarantees, as long as the watchdog doesn't say the system is ready, the actual speed is 0. And under this assumption, the watchdog guarantees that if the doors are not closed, the actual speed is 0. So this is a classical safety condition. And then you can do a reasoning by this assumption commitment ideas, how those specifications can be used to prove properties about systems by just using the calculus as I introduced it. I will skip that for time reasons. Just some final remarks. I didn't have the time to go into a lot of details what I was presenting. I just wanted to give you an idea that if you want to engineer cyber-physical systems, you need a number of ingredients. One thing is abstraction. And in this approach, abstraction is interfaces. Everything is done by interface abstractions. Another ingredient is modularity. Modularity you need of composition and of refinement. And again, abstraction and modularity is achieved by the notion of interfaces. Then you need semantic coherence, which means you have to understand how state machines relate to interfaces, how architecture relate to interfaces, how architectures of state machines are related to state machines of architectures. That's an interesting thing that has to do with this rule that I've introduced. It doesn't matter whether we move from an architectural element, a description by a state machine, and put it together to big state machines in the architecture, or you do the interface abstraction first and put together the interface abstraction, and you need, for instance, semantic coherence by extending deterministic models to probabilistic models without having any violation of the properties you have seen at the deterministic level. And so you get 3 forms of expressiveness: set theoretic and logical, continuous models for control theory, and probabilistic models. And another important angle to look at that is the following. You have a triad of modeling. What you have seen is I have given you denotational models, which are the mathematical models you deal with. In the interface example, these were this mapping from histories to sets of histories, which is a mathematical model of system behavior, with strong causality and what else you need. We have a logical system properties. This was specifications. each such behavior can be described by a logical formula. Having the logical formula, you can write specifications. Having specifications, you can do deduction, because this is predicate logic, so you can immediately do verification, and you can also study transformations, refinement. And the third element in this triad is notational. Of course, you will not be able to describe systems just using mathematics as I introduced them or logic as I introduced them. So you need notational special concepts like diagrams. You have seen a number of diagrams, and we have more. I just pointed that out. And you need tables, for instance. Often tables are a very nice way of describing systems and their behavior. Or you can also use formulas. Last remarks. This modeling framework was initially called Focus. We work on it since 15 years or 20 years now. We have a tool which is AutoFocus 3, which you can find on the web. It's a free domain. And a lot of the concepts, not all of them, but a lot of the concepts I've introduced are directly supported by the tool, so you can do the development. We have done a number of developments in the tool using this calculus, and there are other semantic foundations which are a little bit different. One of the old roots is, does someone here still know SDL? The old guys say no. Of course, what we have done is also modeling bus systems, CAN flex rate. We have studied also a little bit the relationship to UML and SysML, and that you can very well express the shortcomings in UML and SysML using that approach, and you can use new ideas like service-oriented architectures. And here you see a book we have published last year, which comes out of a project where a lot of the methodology is explained in details, and here you see the link to AutoFocus 3. That's it. Thank you very much. Thank you for listening.
Questions?
Yeah.
In your experience, is the industry responsive to you mentioned the architecture is not well defined, and are they open to changing always?
That's a very interesting question, and the answer, there are several answers to it. First of all, of course, you have no chance if you go to industry, you will talk like that. They sit there and say, ooh, what should we do with that? So you need translators. And the way we work, I'm just working on the foundational work we are doing. I had to be giving you a talk completely on the more applied work we are doing, which is a different. But let's give a simple example. It's not so simple. A typical example, the mode how we work, or the style how we work. For instance, this feature interaction stuff. There was an incident 14 years ago in our work with an industrial partner, where we had it was not a car which was in the series, it was a development car, where we realized that there was a feature interaction between the air condition and the braking system. And we said, hey, we have to understand that. And so we started to try to understand what's going on. And the challenge was, how could we, on one hand, give independent, isolated description of the different functions in the car, and nevertheless also describe how these functions interact. And so we did, in parallel, a number of investigations in the car industry about feature interaction we found there, and developed at the same time this more theoretical model. And finally, we published some papers in prestigious journals in giving the theory how to capture feature interactions. And at the same time, we worked with the car industry, and some took over the ideas as an idea to work out a description of their functionality in that way. For instance, in this development, it was not only us, but it was also us influencing that. We came up and said, the car industry, you need someone who is responsible for functionality. In the old days, they had only responsible people for subsystems. So there was somebody who was responsible for the for the CPU in the door. But nobody was responsible for functionality. So we said functionality is an issue in its own right. In the organization, you have people that are functionally responsible, a function engineer, say. And now the car industry introduced step-by-step the function engineer, which is a bit away from the theoretical results I was talking about, but it was very much triggered by the insights we gained from that. And we have 2 or 3 companies we are working with which step-by-step introduce, for instance, the idea of a functional hierarchy. So I think we have to accept that the advance in the research we are doing and the amount how it is triggered to practice is not so closely coupled. There is a kind of a delay there. But I'm absolutely convinced that we have to have a deep foundational understanding of what we are doing. And if we give the industry half-baked approaches like UML, this is crime, because it will not solve their problems. And even to some extent, it will make their problems even worse. And in the end, they will give up the idea of model-based development, because they said, I tried that and certain things didn't work. Therefore, I think you have carefully to distinguish between working out the foundations and an understanding at the academic side, doing the transfer to industry, but at the same time looking at what we also do, looking at the urgent problems of industry and understanding where the problems come from and trying to mirror them back in our foundational work. Is that an answer to your question?
Any other questions? Yeah, go ahead.
I had a question about this strong causality, because you mentioned you had a slide or 2 on how to adapt the framework for continuous behavior. But what's the analog of strong causality in the continuous side, where you don't have this sort of
Oh, that's
discrete time?
a difficult question. I don't have a complete answer to that. First of all, you could, of course, introduce this idea rather at the level of continuous systems, which just means that there's a delta. This +1 is replaced by a real-time delta, which is larger than 0. And
This is the theory of that, both in information theory and systems.
actually, if you look at differential equations, often they ignore the delta. And that means that they don't distinguish between input and output. And that makes sometimes some of the calculations a bit simpler. But on the other hand, they ignore causality there. And that's an interesting question. There's a lot of interesting work on that. I discussed this a little bit with my colleagues in other disciplines, particularly in physics. And some of my colleagues from physics explained to me that causality is the most important principle in physics. And it means that you have a kind of a time flow, and dependency follows a time flow. And this is just reflected there. I can explain to you that if you take away strong causality and only causality, this modularity of composition doesn't work anymore. This is also the reason that in the work of Gerard Berry in Esterel, he has something which he calls causal loops, and there he has to work hard to get rid of them. But of course, having this kind of causality has also a few disadvantages, because delays accumulate. So it's a little bit of a trade-off how you do it. We decided to do it that way because a lot of the mathematical problems get away, and the whole approach is simpler. So it's simpler to teach it to engineers. And they understand it anyhow, because any engineer knows that there is a little bit of a time delay until a system reacts to some input.
Actually, if you do that, all these causal loops go away, and also the Zeno phenomena go away.
Not completely. This is one question. The question is if you have a delta. Like if you vary the delta, then you could say if the delta gets smaller and smaller in every time, then you even have the Zeno phenomenon.
If you look at some of the classical examples for the Zeno phenomena, they don't introduce delay. The moment you introduce delay, this thing stops.
Zero goes away if you insist on a lower bound for your deltas.
So it's a question whether in physics, right, if you can actually, I mean, I asked it be another, right? Give me a real experiment. Come here and do it. Real physics, so I can see it.
And the question is very deep. I'm not a expert in physics, but it's very deep. If you look how you calculate the movement of the stars, in a certain sense, there's no causality assumptions. There's only assumptions that you have the rules how they behave here. But now, if you assume that you bring into this movement of the stars, you bring in an event. You take a nuclear bomb and you just do an explosion, so a star disappears. Then, of course, there will be a causality, how long it takes until the other stars, excuse me, my formulation, realize that the star is gone. So I'm sure there is a delay, but this is not captured in the classical physics. And now we realize that physics only works with models. And these models only capture certain aspects. And you can have a delay-free model and a model that captures delays.
So it's captured in general relativity. Right? And that was brilliant. But anyway, I have some more practical questions. So, how far you can go just to state machine?
Sorry?
How far you can go just to state machine?
How far you can go just with state machines?
Because this is fine for embedded systems, but if I work with the physics of things and so on and so forth, state machines are not enough.
If you work with physics, of course, you have to find a way to model physical effects.
But state machines, they are not enough. So I get into hybrids.
I think for many physical effects, state machines would not be the right model.
Right.
So actually, in some sense, these interface models, they are related to state machines, but they are more abstract and more general than state machines.
Because what people have done for physical systems is they take the physical system and they try to find critical boundary states and so on and so forth, and then they can find the state machine to present particular critical conditions. But that runs into other difficulties. It's not that simple as a state machine.
Yeah, and I think you have certain environment conditions in which you wouldn't like to model by state machines. I think state notions could help a little bit. We have done some work in understanding.
Well, we have state notions, but they're not state machines. They're other states.
That's exactly what I mean. We have done some work in the field where you have a car and you have a street, and you want to understand how the street interacts with your car. And then, of course, I wouldn't like to understand the street as a state machine. But I could understand the street as having states. But whether I would like to understand the street as having state transitions, I'm not sure.
Any other questions?
Going back to the industry, are you applying any of your work to industrial problems right now?
You mean to what extent we
Going to, as you said, Baras or whoever, and then picking up a use case and
we do that. We have a number of patterns how we work together. Some work is done by the PhDs. We do case studies. We look at that. We have, for instance, done for a few years ago. We have done a huge case study in the verification of a real system. So we took a system as you find it today. We did a complete verification. It was a system for the so-called e-call, the emergency call, which will be a feature in the car which has to be there by law due to the European Commission. So if you have an accident and your sensors in your car find out that you have an accident, then an accident has a certain severity, then an emergency call is automatically sent out. And we have really done the full verification, which took us months and years at the level of a flex-ray bus, having an operating system on top of that, having the running application on top of that, in code written in C, and also having the modeling part where we modeled all the stuff. And we have done that, and we've done that also together with industry. Bosch was involved. So this was a brute force experiment. which showed that it takes an awful lot of work to do it, and it has to be differently structured. But we also look at examples which come from industry, and there are many different ways of doing that. Sometimes we look at the problems they have and try to understand and try to see where we can help them, but sometimes we really develop our own ideas and go to them and say, look, we have an idea, why don't we use it that way?
Any interest or any interaction with the manufacturing industry, production systems?
Not deeply. Most of the work we do, the main work we do in the automotive industry. We do some work in the energy sector. We do a little bit in the health sector, a bit more in the avionics sector. We are involved in some work on production. Actually, we run a Deutsche Forschungsgemeinschaft project, which is roughly like NSF, on production systems currently, where we try to carry over the ideas more specifically to production systems. We do that with a chair in mechanical engineering. So there is some work, but we did not work in projects that only at a few points we work directly with production industry.
There is work that applies similar ideas to processes, the integration of processes for manufacturing, including logics and things like that. This has been going on for years.
There is.
Not exactly this formulation, but very similar formulation, even here. And then the big dream is to bring the two together. So you can go from system design to manufacturing and back. Anyway, please come back at 4 if you're interested for more discussion, or make an appointment to see Professor Broy. He'll be here today and tomorrow. Thank you very much.